Okay, recording has started.
Thank you. And guys, if you can help, try to remind me to take roll. Um, maybe after uh, we'll give folks a chance to sign in. I think we still have a few that are missing, but um, let's somebody remind me to take roll after I show this first PDF. Okay. All right. Let's share our screen. All right. Okay. So pardon the notes on here. So again, this is just an introduction to Big O notation. Now, you guys may, if you've had me, we talked about it briefly. Um, and, really what Big O is we are classifying algorithms, right? We're not so much worried about, you know, uh, some of the, I guess you could say, the nuances as far as, like, for example, if I have two for loops, but they're not nested, right? So that would be, 2 times n. We're not interested in those sort of things like constants. What we're interested in is labeling or bounding, what's called bounding a function or a program, right? Underneath, right? Underneath, or it grows at the same rate, right, as one of these classes of functions. Okay. It may be offset a little bit, but we're interested in the growth rate. Okay. So, it may be that our algorithm is n squared plus one, for example, but the overall growth rate is going to make that one nothing. Okay. Um, so if you look here, let me put on my glove. You'll see, we have some of the ones that you guys are familiar with are, though I didn't list here, big O of n. We also have, we have big O of n, we have big O of 1, right? But the ones that we're really interested in are, you know, in this class, we're interested in this guy here, which this is the same. LG is just another way of shorthand of uh, log of 2, right? Base 2. So that's, this is like your binary search algorithm, right? Where you're dividing a problem in half. You just divide it in halves. Okay. And each time you're dividing it in half on one side or the other. Okay. So that's a typical, algorithm that's big O of log n. And then, you have something a fairly amount worse is n squared. Of course, I have that n there in the wrong spot. That would actually go here, right? Um, and let's see here. We have uh, something a little bit worse, right? A to the power of n. And then we have something crazy, right? I mean, this is absurd. Something that's like n factorial to the n factorial. Okay, you're not going to get through too many n's before you just run down, use all your stack memory or something on an algorithm. Okay, so we're interested in identifying these classes, right? Classes of algorithms, and another one, like for example, a nested loop, right? That's Here's an example of a nested loop. Okay, here's an example, right, of a for loop. That's just big O of n. You're going through, and normally you're going through like an array or something, some sort of collection of items in sequence. Okay, and then here, of course, is an example of big O of n squared, where I and j. This actually should be a 1 down here, not a 0. You know, each time, the inner loop is based on the outer loop. Okay, and we'll go over a little bit more examples of this, right? But now, what's important is um, now the inner loop either needs to be an independent variable. Well, it depends. For it to be n squared, right? the inner loop has to be dependent upon the outer loop, and both of them are based on n, right? But if I have, say, an inner loop that is m, for example, right? So that ends up becoming a little bit more challenging, right? So maybe m is not related to n, okay? So that might end up being, you know, big O of n plus m, for example. And we'll see some examples of this. Also, if this inner loop has like a constant, like say for j equals 1, and then there's literals, right, to 5. So irregardless of what n is, if this is a 5, this is not big O n squared, okay? This is the same thing as having 5 steps in here, 5 lines of code. So that would still be big O of n. Even if you have a nested loop in here, it's only when that nested loop is dependent upon the outer loop, you know, the control variable here, which is n, okay? I'm sorry, I, which is based off of n, okay? And we'll see some examples of this. Another kind of problem, though, that's really, you know, that's kind of, you know, or an example of big O of n cubed is if we do matrix multiplication, right? Now, I'm not going to, we don't have time to go over, you know, matrix multiplication other than, you know, it's going to be what? This term, 1 times the 5, plus what? 2 times the 6. And so you're going across this way, and then you're going to the same thing for these guys here. Then you're going to the same, you know, so you're multiplying these across. Well, the way that we do that is through, you know, a triple nested loop. Okay. So these are just examples of algorithms that are like this. And let me get Zoom out of my way here. Zoom always has a tendency to get in my way for Windows. All right, so I actually found a nice little video. It's not long, and it's not the majority of this, right? So let me, well, actually, I think I already have it up. We'll take a look at this. This should look familiar. Does anybody remember, though you've never seen this video before, Zoax.net, whenever I was teaching sorting algorithms, right, in CS1B, those of you that had me, you might recognize this this intro here, okay? It's not the same, though, as the ones I've shown in CS1B, okay? And if you're having a hard time hearing it, then just, you know, then just, I guess maybe turn down my volume and then click on the link that's inside the PDF there that I've posted, okay? All right, so let's watch. This is like 6 minutes and 47 seconds long.
Lesson 6, big O, big omega, and big theta notation. When we speak of an algorithm's efficiency, we want to determine its scalability. That is, we want to know that when the algorithm is applied to a large data set, that it will finish relatively quickly. We can also talk about how much memory an algorithm requires, but for now we will focus on speed. We measure an algorithm's speed in terms of the growth in the number of operations relative to the input size. For the linear and binary search algorithms, for example, the input size is the number of elements that we are searching. Typically, we will use the letter n to represent an unknown input size, and we will talk about the growth in terms of n. To formalize our ideas of growth, there are 3 types of bounds that we will address here: big O, big omega, and big theta. The definitions that we will use come from mathematics and are used to relate the growth in one function relative to another simpler one. Here we have the graphs of 2 real functions, f of x and g of x, given by the gray and dashed arrows, which we use to indicate that the functions continue indefinitely. The function f of x is more complex, and we want to measure its growth in terms of the simpler function g of x. More specifically, we want to find a constant such that when we multiply it by the function g of x, it will bound the function f of x above from some point downward. Assuming that the graph of f of x does
Okay,
not.
let me pause this for a moment. So what he's talking about here is, let's say that we have a simple function like, I don't know, maybe f of x. That's the function that we want to see, how well it, or we're trying to compute the big O for. Okay, so if function of x is equal to, I don't know, maybe 2 times x plus 2, for example, right? Or maybe it's 2 times x squared plus 2. So early on, this thing may wiggle and waggle, right? So here, if I want to bound this by, right, I want to have as close to a similar growth as, say, for example, big O of x squared. Now, so here, g of x is, if g of x equals x squared, for example, what we're trying to say is, this function here, by the way, is quite simple, but, it's a little bit more complicated than this x squared. So, we're looking to put this guy into a class. And what it's saying is that at some point, right, at some point along this line, right, we can find some way to multiply some real number. It doesn't have to be an integer. Okay. So what can I multiply x squared to so that I always know that no matter what, it's going to map out to be higher than 2x squared? Can somebody give me an example? How can I multiply g of x? What constant can I do that with? And g of x will always be, let's see here, greater than or equal to f of x. Or if you write it the other way around, it's f of x will always be less than or equal to g of x, right? And usually it is including, it could include 0, right? Or it can go all the way, it can't include infinity. You can't find infinity. But so can we find some number, some constant to multiply x squared by so that no matter what value x is, it's going to be greater than this f of x? Anybody daring enough to guess this?
I'm going to go with no.
I can't hear you. What?
I'm going to go with no, there isn't an x.
I mean, not an x, a c. Is there a c that I can?
Oh, sorry.
Yeah.
For just x squared, I'm going to go with no. Because if you plug in 0, it's always going to be 0 no matter what c you have. And then f of x is 2.
I just have to find one. I just got to find one number in this range to make this true. Okay, so
I guess I don't understand your question then.
All right, so how about I give the answer and then maybe we backtrack. So is there some constant that I can multiply x squared against, some constant c, so that when I multiply it against this x squared function here, to where this guy will always be greater than or equal to 2x squared plus 2.
And that's for all x?
For any x along, given this c. So for example, right, if I multiplied x squared by 3, is it not true that no matter what x value I use, that this side here will always be greater than or equal to?
What about x equals 0?
Well, I don't have to prove every one. That's the thing you got to remember. So the definition of this is that I can find one c somewhere along the line. Okay? It doesn't have to be every single number on that number line. You see? So that's the thing I think you're not getting, is that for asymptotic notation for big O, okay, I just have to find one number. Now, everything everything past that one number, in this case, it's 3, right? Everything past that number on this number line will suit it, okay? Now, I'm not asking you to find the minimum number either. Just find some number on the line here where if I multiply g of x, then it will always be greater. So we're going to, that's what's called bounding my function underneath that function, right? So given this value at this point, right, at this point right here, then that 3 times x squared will always be greater than, let's see here, over here's x. So x, so here, given this function, well, past this point, right? That's the point of intersect. So here, there's going to be some number, some value. I mean, this will equate to some value in x, right? So the important thing is we're trying to, and the reason we're trying to find this upper bound is so that we can simplify this to know that this guy falls in the family or the class of x squared, big O of x squared, you see. Now, you knew this before, right? You knew that, okay, I take off constants and take off multipliers, right? Because this becomes the dominant term at some point. And even if it's 2x squared plus x, I would argue I could find an x, or I could find a constant at some point, right? That if I multiplied x squared by, that it will always be greater than that. Even this, right? Let's see, what if is 3 times x squared greater than 2x squared plus x? Yeah, right? Okay, so, and that's what I'm saying. This is a difficult topic. And we have an entire series of classes, CS, we have CS and math classes. They're kind of the same for discrete structures that teaches this. So, you know, right whenever I was getting ready to, and I was preparing for this class, you know, a few weeks before school started, you know, I'm like, oh my God, you know, most of you guys have not had that. So I'm not going to lay that on you, okay? But it is important, in my professional opinion, it's important that you at least understand that if you're going to choose a data structure, right, to solve a problem, you, in most cases, not every case, but in most cases, you want the most efficient data structure, okay? Now, as you know, right, if I want to sort, you know, an array of items, depending upon which sorting algorithm I use, I could have what? If I use the insertion or selection sort, what's the big O for it? N squared, right? But what's the big O for the, well, actually, we have another class of, you know, like the quick sort or the merge sort. That's those are in the family that's faster than N squared, okay? So it's important to choose, you know, a data structure, but now those actually have, you know, there's no free lunch, right? So a lot of times to do things like divide and conquer, you're going to use more memory. And if your data set is just really small, like, you know, the number of students in this class, if I want to sort your final grade, maybe I don't, you know, it's probably appropriate to use a bubble sort or a selection sort to, you know, to sort things, okay? Because it might be more expensive to manage a merge sort or, you know, some sort of quick sort, right? Maybe it takes longer to manage that code, okay? Or maybe it ties up more resources than what it's really worth. Of course, it's kind of hard to do that with a small sample set, you see. Okay. All right, now we're going to go over this several different ways. So if you don't get it right away, think about it. Okay, we'll watch the video, and then I've got some more slides that we're going to go through that covers the same thing again. Okay, so let's just see how we can make out with this. Let's see, is that going to Will that work for that? No. Let's just stop the annotation.
Intersect the graph of c times g of x after the point x0, we know that the graph of f of x remains in this white region for all x to the right of x0. In this case, we say that f of x is in big O of g of x. Formally, we say that f of x is in big O of g of x if there exist positive constants c and x0, such that f of x is less than or equal to c times g of x for all x greater than x0. On the other hand, we could bound the function f of x from below, like this. If such a constant exists such that c times g of x bounds f of x below from some point onward, then we say that f of x is in big omega of g of x. Formally, f of x is in big omega of g of x if there exist positive constants c and x0 such that f of x is greater than or equal to c times g of x for all x greater than or equal to x0. So there are constants such that g of x bounds the function.
All right, so let's see if we can find an example of that, right? So we found an example. So we've already shown that given C, now look, these numbers are different, right? C1 and C2. Okay, C1 and C2, and so this is big omega, right? Let's see. Did I draw that right? So this is big omega. And this one over here is big O. Okay, and so this would be, this is big omega of x squared. That was the one we were talking about, right? So if f of x is equal to 2x squared plus 1, we'll simplify things. Can we, we already said we can find a constant. So if g of x is equal to x squared, right? I want to see if I can get this in the class of functions upper bound by this, or actually n, right? We usually use n. But big O of x squared, we know that's a class. That's a class that we're bounded, that this function f at this point will always be under this g of x, right? But that's this g of x. So this is the original g of x, the dotted line. But if I multiply it by some constant, we found one, right? We probably could have gone 2.1 and done it. But, I only had to find one. So let's, we don't need to blow a fuse, to try to see, okay, what's the smallest? But, 3 times, if C1 is equal to 3, and 3 times x squared, is g of x equals x squared. Okay, how did I didn't mean to undo all that. Let's see, this equals 2x squared plus 1. So here, I would argue that this will always be greater than or equal to 2x squared plus 1, right? And and any number past this, right, all the way up to but not including infinity. Okay, so here, so if x, now we find some x, right? It may not be this x down here. It may not, if this is the x line on the bottom, it may not, it's probably not going to be 0. X can't be 0. And it may not even be x is 1. Okay, but we'll find some starting point. So if I want to work this, then I'm going to say, all right, 3 times x squared, if x is equal to 2. So 3 times 4 is equal to 12. Is that going to be greater than or equal to 2 times 2 squared plus 1? Which is what? 2 times 4, 9. Do I have that right? Okay, it's possible I haven't. Yes. I misadded that, right?
It's correct. It's 9.
So, I found one. I don't have to find the smallest one. I just got to find one. I just have to find one. okay? And so then my x down here at 2, and that may be kind of hard to see. So it's what this is saying is that actually here, right? So let's pretend that's 2, okay? Now you probably could solve for 0 and find the actual, or run some kind of limit or whatever on to find the smallest. I'm not interested in finding the smallest right now, okay? I just want to understand the idea. So this function, and I know you can believe this because you can tell by looking at it, right, that this is the strongest dominant term. So that's going to be big O of x squared. I just proved it, okay? I proved it by an example, right? So we'll look at the formal definition, and I'm not going to ask you to memorize the formal definition. But what the definition says is that once I get started here, it's impossible to find a number past the number line on this 2 down here to where the statement that f of x will be bound, the upper bound of that is going to fall underneath this guy here. C of 1, well, I'm sorry, C of 1 times G of x, okay? And we know that this times x squared, if you take big O notation of it, it's just x squared, right? So here I've shown that f of x is, falls underneath G of x, okay? Because at some point, right, G of x will climb over it if, given this constant here. All right, now the other thing is this part here is omega, right? Now what omega says is the opposite, is that we can find a different constant. Obviously it's going to be smaller than C1, okay? Can we find a different constant such that if I multiply x squared by it, that this guy will be less than or equal to my function, which is 2x squared plus 1. Okay. Now, if you want to know how to easily do that, let's, if you use decimal numbers, right? If you use your constant C2, if you make it like some kind of a fraction, then you end up guaranteeing that this guy here fits. Okay, so let's try my constant equal to 0.1, right? Isn't it kind of easy to figure that out, right? So what would let's see here, if my constant is 0.1, right? And if I multiplied over here this function here, well, let's see here. If I multiplied x squared by 0.1, right? You pick some x. Let's say x was 2 in this case, right? So, you've got 4, but what is 0.1 times 4? Or actually, is that right? Wait a minute. Is that not? Yeah, that's 0.4, right?
I think so, yeah.
So this would be 0.4, right? So to keep my, my expression true here, what if we multiplied 2 times, let's see, x being the same number over here, 2, right? If x is equal to 2, we got to make sure we don't forget that. So 2 times 2 squared plus 1. So what's this one? So which one of these has precedence? Is it the exponent? Or does it matter?
I think it's the exponent.
Okay. So that's a 9, right? So I've just proven that I could find a constant, right? I just have to find one. I don't have to find all of them, okay? So we're not trying, so we're guaranteed that any constant lower than this, this thing will be lower bounded. And so this f of x will always be lower than anything in this range that falls up underneath this line, you see. Okay, so that's, you know, now you're not changing g of x. That's got to be the same. Okay, that's got to be the same. All right, let's go ahead and let him finish his video.
F of x both from below and above, then we say that f of x is in big theta of g of x. Of course.
All right, now what he just got through saying was, okay, actually, so big theta. He just gave an example of what big theta is. And what big theta is, let's go back and let him give his example again, because I actually interrupted him.
x0. If there are constants such that g of x bounds the function f of x both from below and above, then we say that f of x is in big theta of g of x. Of course, the constants in this case are different, so we have labeled them C1 and C2 to clarify that. The x0 that we choose can be any value that is far enough out that f of x doesn't intersect either C1 times g of x or C2 times g of x anymore, and remains in this white area. Formally, we say that f of x is in big theta of g of x if there exist positive constants C1, C2, and x0 such that C1 times g of x is greater than or equal to f of x, which is greater than or equal to C2 times g of x for all x greater than or equal to x0.
Okay, for those of you, so for those of you losing your mind right now, okay, you know, I'm a visual person as well. So all that's saying is that big theta, right? Big theta is that if there is a if there's a constant, right? Well, if let's see the constant times g of x can give me the lower and upper bound together, right? That's going to bracket this thing. Okay, so we know, hey, look, the worst case is going to be that bottom line here, right? I will never, if this is time, right? If this line here, the y-axis is time, I can guarantee that at worst, my function of x will you know, at some number, you know, some number of elements in my, you know, some size of my data set will operate in this time frame here. Okay.
We say that f of x is in big theta of g of x if there exist positive constants C1, C2, and x0 such that C1 times g of x formally.
Okay, I mean, it's kind of hard to catch that. So here is that if we can find two constants, one that bounds, you know, because we're interested in function of x, right? And we're interested in classifying that function. In our case, in this class, we're interested in classifying our data structures for sorting, right? I'm sorry, not the data structure itself, but the sorting algorithm or the search algorithm, right? We're interested in, you know, classifying that algorithm. And so if we can find a constant C1, now these two can't be the same, right? C1 can't equal C2. If they do, I mean, because then it's like it's the same, right? So there needs to be two different constants that one ensures that my function will always be under it, and another one will ensure my function will always be over it. Okay.
White area. Formally, we say that f of x is in big theta of g of x if there exist positive constants C1, C2, and x0 such that C1 times g of x is greater than or equal to f of x, which is greater than or equal to C2 times g of x for all x greater than or equal to x0. So far, we have shown what the situation looks like for general real functions. For algorithms, the input size is generally a positive integer, like the size of an array for a sorting algorithm. In this case, we can think of our f and g as functions on the positive integers. In mathematics, x is used to signify a real variable, while n is used to signify an integer variable. Like Hungarian notation in programming, this notation allows us to see more immediately what is going on, so we will use it. Using this notation, here we see the graphs of two example functions f of n and g of n, given by the solid gray and hollow black dots respectively. Notice that the graphs are made up of single dots instead of curves. This is because the functions are defined on integer values. Just as we had for the real functions, we can have constants such that when we multiplied g of n by them, we bound f of n from some point onward, and the definitions are analogous. Here we have a constant multiple of g of n such that its graph is above the graph of f of n from some point onward. The last value that puts the graph below the graph of f of n is 2. So we can set n0 to 3, and we have f of n in the white areas below the graph of c times g of n from 3 onward. This is how we define big O of g of n. Formally, we say that f of n is in big O of g of n if there exists a positive real number c and a positive integer n0 such that f of n is less than or equal to c times g of n for all integers n greater than or equal to n0.
Okay. Now, I actually misspoke earlier. It does not include 0, right? So it does any number above 0. Now, he's talking about integers. It's hard, sometimes it's hard to find like a big omega that is an integer, okay? So those kind of functions, it's easier to to find a big omega if you can just use a fraction, okay? So for real numbers, so it's a little bit more challenging to do it with integers.
N0. Likewise, we might have a constant multiple of the function g of n such that c times g of n bounds f of n below from some point n0 onward. In this case, f of n is said to be in big omega of g of n. Formally, we say that f of n is in big omega of g of n if there exists a positive constant c and a positive integer n0 such that f of n is greater than or equal to c times g of n for all n greater than or equal to n0. Additionally, we can have two constant multiples of g of n that bound the function f of n on both sides from some point n0 onward. Here again, we say that f of n is in big theta of g of n. Formally, we say that f of n is in big theta of g of n if there exist positive constants c1 and c2 and a positive integer n0 such that c1 times g of n is greater than or equal to f of n, which is greater than or equal to c2 times g of n for all n greater than or equal to n0. Our purpose at this point is simply to give a visual impression of these bounds, along with an exact definition. In the coming lessons, we will give concrete examples of how they apply to specific algorithms so that these ideas become clear.
Okay, so if you guys want to explore this more, you can follow this video series. But again, my intent is not to make you math-proof professionals. That's this class just can't do that, right? Because they're just we still got to study some data structures. But it's important, right, that you at least be able to understand these terms when you see them in the descriptions, and maybe be able to work a very, very simple case like what I did. Okay, so if we take a selection sort, right, can you find a constant that if your selection sort, if it's maybe it's something like, maybe it's you've got some extra stuff in there, and maybe it ends up being you have like your selection sort, right, your 2 for loops here for your algorithm, and maybe you do outside of this in your algorithm, you've got some C out statements down here as part of the algorithm, right? So maybe you got like 5 of those lines, or let's just say 2 C out statements here. But this encapsulates your entire selection sort algorithm, right? So if you were to measure this, this would be like probably x squared or n squared plus 2, right? So can you find a constant? So if we pick a g of x, can we pick a constant such that this guy will always be greater than this? I just did, right? And so, and then can we pick a constant, a different constant such that it times g of x would always be lower than? And the answer is yes, you can. So what you can do is, you know, if I ask you to tell me, hey, what's big? Give me an example of big theta, right? And I'm just gonna murder that theta sign. Okay. I think do I have it right, or does it go like this? Okay. So the theta sign, big theta, means that you've got both of these, right? You've got some kind of function like this, and my function falls in between these two. Okay. So let's see here. All right, so let's go ahead and jump and finish up the rest of our slides. Stop the annotation here.
Professor,
Yes.
it's time to take roll. You said to remind you of roll.
Thank you so much. See, I get into this, right? Only because it takes. I mean, this takes a lot of thought, right? It's not an easy concept. I would say in computer science, for me, aside from calculus 1, you know, I mean, calculus 2 was easy for me. Calculus 1 was a nightmare. I ran out of instructors to keep retaking it. Okay, at the school, at the university I was going to, it was embarrassing. I finally made it, right? But the point is, in my opinion, in computer science, this topic was always the hardest for me to grasp because I was never good. I was never really, you know, I was never good, not even great, not to mention great. I was never really good, right, at determining limits and solving these equations and polynomials and, you know, doing proofs. My gosh, when I was getting my master's degree, there was a theory class. You guys get your master's degree, you're going to take a theory class. And you're going to learn what's called non-polynomial and polynomial, which, you know, NP complete and incomplete, and do all these proofs. My goodness, I survived it. Okay, I made a B. Class started out with 72 students, right? We graduated 23 out of that class that semester. Okay, and I just survived, you know, by the skin of my teeth. I think I made a B in that class. But you're not going to escape these terms, and that's why it's important that you at least get the basic, right? You don't have to be, you know, you're not going to be spitting out formal proofs for me, but you at least need to be able to talk a little bit about these. Okay. All right, so let's jump over to our PDF for Big O, and we just got through watching that, and you just reminded me, and I just completely gapped you off for taking roll. So let me stop sharing, and let's take roll. Let's see here. Attendance. I forgot to reset my router last night at 3 o'clock, and my entire internet's been slow today. Okay, sound off when you hear your name, or chime in the chat box, and you guys tell me if somebody chimes in. Okay, Joshua Acosta.
Here.
Jared.
Here.
Amir Parsa.
He's here. He's in the chat.
Okay, Edwin.
I'm here.
Victor.
Here.
Simon.
Here.
Cassandra.
She says she's here. He's in the chat.
Okay, Tyler.
He's in the chat.
Okay, Paolo.
Here.
Grant Goldsworth.
Right here.
Okay, George.
Hello.
Okay, George. Isaac.
I'm here.
Nicholas.
Here.
Grant Kelsey.
Here.
Anish.
Here.
Rex.
Here.
Ayoko. All right. Okay, Carson.
Here.
Eric.
Here.
Sean.
Here.
Nima.
Here.
Felix.
I think he told me he went to the bathroom like 5 minutes ago.
Okay, so you saw him in the chat?
He messaged me 5 minutes ago.
Okay, all right,
Yeah,
Cena.
but he's still here, yeah.
Cena.
Right here, Professor.
Okay, Angel.
Here.
Kevin. Just
Dead.
talk to me. Matthew. Is Matthew here?
Here. I'm here. Sorry.
Hey, Matthew, are you related to Kevin?
No, not by chance.
Okay. All right. Andres.
Here.
Robert Peterson.
Here.
Robert, you got my favorite glasses on?
Not currently. No.
All right. Islam.
Here.
And am I saying that right?
Yes, you are.
Okay. So Connor.
Here.
Dennis.
Here.
Patrick.
Here.
Steve.
Here.
Nicholas.
Here.
Preston.
Here.
And Victor.
Here.
Okay. All right, folks. Everybody's here. I think we had a couple of drops. Okay. All right, so let's back to home. Okay, so all right, share this. Oh, I'm actually sharing the screen anyway. All right, so let's get back to our slides, and then we'll wrap this topic up, and then we're gonna talk about the handout that you guys had, and then whatever time we have left, we're gonna talk about range minimum queries. Okay. All right, so a couple of things. It's kind of not. I mean, it's important that you be comfortable with log. So whenever we talk about log, like the log of n, we normally mean, get my pen here. We're not, it's generally speaking, we're talking about, unless it's specified otherwise. Hold on a second. Let me undo the highlight here. Unless we specify otherwise, we assume that, we're assuming log base 2 of n, which is also LG. And, if you want to try to figure out the log of something, for example, 2 cubed equals 8. What we do is we say, it's equivalent to log base 2 of 8 to the power of 3, or to 3 equals 3. So this is our exponent right here. Okay, this is the exponent that we're talking about. Okay, so these two are equivalent to each other. And, you may come across a case where, it's important to understand these rules, right? With real numbers and log of 2n. So these are, general rules, and, I don't plan on using them in this class, but usually whenever you're studying Big O, they normally throw these out at you. Okay. Okay, Big O, we talked about that at length, but really, these are the formal definitions. Okay. Again, I'm not going to ask you for these formal definitions. I just want you to be able to maybe draw it out and give an example, just like what I did earlier. Okay. Here, this is just another drawing where I've got some constant times g of n. This is just the same thing that was in the video. Okay. And here, all we're doing is, here we're going to show that 3n squared plus 5n is in Big O of notation. So, it doesn't, or Big O of n squared. So it does not, actually this one does include 0, but big, the big theta or big omega does not include it. We'll see here in a minute. But it goes to, but does not include infinity, right? And so you can just run these limits on these things. So the way this works is, if here on the top, right, you've got, here you've got your function of x. And down here, right, if you're, function of x divided by, or function of n divided by g of n is the same thing, same way as writing it this way. Okay, and then you can run the limit as n approaches 0. You can see that as this guy becomes 0, right, you end up with 3. I'm sorry, not 0. As this guy gets larger and larger, this guy gets smaller and smaller, okay? But this guy will never reach 0. You know that, right? This guy will never reach 0. So you'll never get a, you'll never get a number equal to 0. Okay. So here, so the way we factor this out, right, is we have 3, and then we have 5 over n. And then, of course, as n gets larger and larger here, right, this ends up actually at some point approaches 0. So we end up with 3, okay? So in this case, this means that for a very large n, f of n performs 3 times as fast as g of n, okay? Or the other way of saying that is g of n is 3 times slower, right? Takes 3 times as much, 3 times longer to complete that function. So the function will grow not significantly more than the upper bound, okay? So that's just another way of saying that. These are just some examples, right? It's probably good that you at least understand and recognize this, right? If we were to, to sum up a nested loop or describe a nested loop, this is the number of operations it would take, okay, on average. Like say for a sorting algorithm. Okay. Here's summation. Again, I'm not going to go over this, but this is just basically if well, I guess I will. If I equals a, for I equals a to b, function of I is equal to f of a plus f of a plus 1 and so forth, all the way over to b. That's the same way of saying, since this is a summation, right, which you have up here, this is the same way as just saying, I equals 1 to n, and then you just summarize all of these. So these are just examples. Exponents, those are just some exponent rules. I'm not going to go into this, but it's there. Big O discussion. So here, here's where we talked about earlier that there was just some constant, like 8n over here. So if, let's say that, let's see here, it looks like f of n, if f of n is 8n minus 2, is there some constant that I can multiply against this? And the answer is yes, there are. So, which case do you want to study? It says here, worst case analysis is much easier than average case analysis, as it requires only the ability to identify the worst case, okay, input, which is often simple. Also, this approach typically leads to better algorithms, making the standard of success for an algorithm to perform well in the worst case necessarily requires that it does well on every input, okay? So, we can't just take the best time that our algorithm works, right? Because that may only be on a certain, certain set of numbers, a certain data size, right? So maybe our algorithm is only best case for 100 items. You get it past 100 items, then we start approaching the worst case, right? So this is where big omega and big theta, or I'm sorry, big O, big omega, and then of course this would be, if you can find 2 constants, that would bound that up, from the top to the bottom. Okay. Again, these are more examples for you to take a look at. More examples for you to take a look at. Okay, big omega, this is the formal proof for it, formal definition. Again, it's just finding that constant such that this line will always go, always be faster, right, than the algorithm I'm studying, okay, which is, some function of x. Okay, big theta is whenever you can find 2 constants that will give you an upper bound and lower bound. And then these are common orders of magnitude. You can read this on your own, right? We want to stay away. We want to stay away from these guys, right? We want our algorithms. The truth is, this is bad, but it's not the worst case scenario, right? But I mean, go back to sorting. If I need to sort 1 million customers, it's going to take a long time. So that's kind of bad, right? Now, I don't want to use this kind of a sorting algorithm. That's there's a difference between bad and horrible, right? I mean, and this one down here is insane, right? You don't want to do this. So we want things to be up in here, right? Or better yet, in here. Okay. Very seldom do you have big O of 1, right? That just means you don't have any loops. You don't have any iteration. Okay. You might get a few of those assignments in CS1A. That's about it. Okay. Here's just some rules. If you have 2 independent variables, then, if you have 2 checks, so an example could be, let's say that you want to write an algorithm that spits out the min and max inside of an array, right? You want to keep track and find the minimum value and the maximum value and return 2 indices. Maybe you pass some arguments or parameters by reference, and then you're going to store the index of the min and the max, right? So if there's 2 checks, right, in that for loop, then it's going to be big O of m plus n. And if multiple threads, the largest of the 2 dominates, right? So it could be that that's nested. That's big O of n squared. And constants added or multiplied don't matter. So there's an example. You still have big O of n, right? Okay, so this is big theta. This would be an example of proving that is 2n plus 1 is equal to big theta of 2n. Can I find some constant that when multiplied against 2n will be lower than the result of 2n plus 1? And let's see. 3 squared, 2n plus 1, 2n. Okay. So, okay, big O is true. So here is big O for c greater than or equal to 2. And here, big omega of a big theta of 2 to the power of n is true for any value in between or greater than 0 and less than or equal to 2. And you can just work that out, right? So if I were to multiply this guy by 1, right? 2 to the power of n by 1, of course it's going to be less than 2 to the power of n plus 1. So therefore big theta is satisfied. Okay, so if you're trying to solve some of these problems, just try to use reasoning instead of formal proofs. Here's an example for selection sort, right? And you guys remember the selection sort, 2 numbers are compared and you try to keep track of the largest and you pop the largest at the bottom, you swap it, right? So if you go down through here, you keep track, this is the index of the largest. When you get to the end, you do the swap, you bring the 4 up here, you got the 7 here, and then you just go through the rest of this, right? So you just keep going. So here, if you're trying to prove that this particular sort algorithm is big O of n squared, if you remember this part right here, right, that was one of the things that was important. You'll see that each time through the loop, you're having to compare against every single element, but one less than the one time before. So right, so here the first time through you're going through n minus 1 times, then the second time through you 1 less and 1 less and so forth. So this is approximate to big O, or to n times n minus 1 over 2. Okay, so the idea is that we're adding up n minus 1 terms whose average is n over 2, proving that selection sort is big O of n squared. Okay. All right. It's the same thing for insertion sort. Okay. Here's a case where, you know, you've got an algorithm and your task is to determine whether this string here is a substring of this bigger string. And this ends up being, you know, pretty complicated. Let's see, we give the worst case scenario here is the inner loop goes through. Okay, so N and M, you know, M is the length of the pattern that you're, you know, the long pattern, and N is the length of your target string that you're trying to match. And so this just ends up being, you know, this real long, okay, this real long big O computation, which ends up being this, right? And this just gets crazy, right? So here we just get a definition. You guys don't need to worry about this, right? This is just an example of you know, computations for some problems that are, you know, pretty hard to do. Matrix multiplication, we've already talked about that. That's big O of n squared. And I guess that's it. So you guys have probably had way more than what you bargained for in this class with regards to big O, big theta, and big omega, but I do need you to understand the basic premise of it. So while I may not have you do a proof, I may, but I will ask you to give me, you know, try to give me some examples. And the first one is on this, this first assignment. Okay. Now, if you look at your assignment, okay, this first one, I'm providing most of the, you know, the binary search search tree. I'm giving you the biggest part of this. Okay, and so this one is just to kind of get you guys in good shape using C. You know, there's nuances, there's pointer nuances and pass by reference nuances in C. So that's really the two biggest things that I've seen, other than syntax difference for outputting, you know, output to determine. Okay, and so you know, I'm going to go over some examples of that here shortly, to where you guys have, you know, have something to use. Okay, but here, what I need you guys to, all right, where is, so if you go to the actual assignment, okay, you're going to see that there's two problems, right? So each problem's worth 25 points. The binary search tree, okay, that one's due February the 2nd. Okay, I actually moved the Finding City one by 1 day, by 1 class period. So this one for the BST, you have to do two things. You've got to upload a screenshot that shows the result of your make file, or the one I gave you, right? Don't change it. And the output of running your example, right? Of running the code against my test data. Okay. So that's and you just upload that screenshot to Canvas. Now, this has to work inside the VM, not, you know, don't show me a screenshot of it running inside of Eclipse. Okay. So this is what you guys, you know, and you got to get out of your comfort zone. In computer science, you're not always going to, you know, you're not always going to be able to use the language that you're most comfortable with. Okay. And the difference between C and C++ for what we're doing is not that much. Okay. We're not doing anything with templates or classes. We don't need them for data structures. Okay. So that's all that you have to do is ensure that in your directory, right, I go in and I look, if I want to run, you know, maybe I won't do it for everybody, but I may go in and rerun your make file. Okay. Just to make sure, you know, I may do a make clean or run make file -C, and then end up, you know, just clearing it and then running your make file again, just to make sure, that it works. But all that you have to do to prove it is just upload the screenshot, the picture of it making and running. And of course, make sure that your virtual machine, your directory, everybody should have the same directory structure, right? Don't go off the reservation and put something way out there under downloads or something and then, make me have to try to find it. Okay. So the binary search tree is due February 2nd at the deadline that you see. Now, what I'm going to end up doing, right? First, I'm going to go ahead and go over this finding cities one again and the unique submission requirements for it. After I do that, I'm going to show you some of my code for the BST. You guys can take snapshots or whatever, and then we'll use whatever time we have left. We'll take a break after I do that, and then we're going to come back and get into this range minimum query stuff. Okay. All right. Now, problem number 2, the same thing. Now, problem number 2, you're going to have to create your own makefile on the VM. So use the one that I gave you. It's relatively simple. Okay. So, and we're going to cover this problem here in a minute, but I just want to make sure you guys understand there's 2 things you got to do. Okay. Number 1, upload the screenshot to Canvas. Okay. Number 2, the second thing is there's going to be some essay questions on Gradescope. Okay. There's going to be 3 forms. You're going to log in to Gradescope and you're going to open up the assignment. The assignment will say finding cities essay question. Okay. I haven't built it yet. I got to figure the thing out. Okay. And I've got to do that like in, about 48 hours, right? Because I want to have this set up so you can look at it and we can talk about it next class. Okay. So I'm watching little tutorial videos on how to get this going. Now, Gradescope is going to help me get your assignments graded in a timely manner as opposed to it taking like 2 weeks. Okay. So it's really important that that you guys, we all learn, both of us learn how to use it. Now, for the essay questions, there's just 3 forms. You'll fill it out. Okay. Now it's important to know, right, that one of the capabilities of Gradescopes is that it compares your answers with other students and it gives a overlap percentage. Okay. So on these 3 questions, there may be a little bit of overlap between each of you, but I'm not interested in you copying somebody else's answers. Okay. I want to know what you know. I want to know your approach. So when you're answering this question, there's 3 of them here. Number 1, I want to know, I want your high level description. Just 2 sentences. Okay. In the handout that I gave you guys that you have available to you, I give you an example. Now, this may be a little bit overkill. Okay. Actually, not this one. There is another handout. Let's see here. Let me pull it up. Go back to it. I believe it was, is it assignment policies? I believe it is. So here was an example. And guys, this is actually not too bad, right? That's a high level. Here you get into, the specifics of it. Now, again, I'm not looking for, this much. I'll be happy if I get this much out of you guys, right, for that assignment. And then, of course, for the runtime, that'll be a 3rd and separate entry. You'll give some kind of analysis. And if you open up Mallet, guys, all you got to do is reference some stuff in Mallet. So for the binary search tree, right, we go in here and let's see, where is, it tells you in here that it operates at big theta. It's somewhere in here. I don't have it earmarked or have it bookmarked. Binary search tree. Let's see. Let me see if they're. I don't think it. I don't think they call it theta. I think they use the symbol. Yeah. All right. So
maybe you can just type in big.
big.
Yeah.
No, it's that symbol. Let me see. Let's see if we can find it. Let's take a moment. I think it's analysis. It's under analysis.
I typed the symbol in the chat for you, so if you want, you can copy paste that in.
Okay, let me go through a few more pages, and if I can't find it, I'll go that route. Here it is. Okay, so binary search tree analysis. Okay, the performance of search algorithm depends. Okay, so this is searching the tree, right? So you've got see, searching the tree within nodes. Okay, the worst case, T is linear. That is, T is one of these forms, and it ends up being big O of N key comparisons. Okay, so that's not much. That's not any better than a linear search. Let's see here. Well, that's if the tree is that if the tree is sort. Let's see, is there a requirement for it to be? Yeah. So binary search trees, they are going to be sorted. Beliefs, you know, you're going to go all the way down the left-hand side if you do what's called in order, and we'll take a look at that here in a moment. So you can look at this and look at this analysis, right, on some of these. Again, I just want you to make a stab at it, make an effort. And if you don't understand it, say, you know, I don't understand, but I do know that binary, well, you know, you're not turning anything in for binary search trees other than your screenshot of your code, okay? Let's see here. All right, now one of the things that you I want to talk about you guys with is traversing these trees. Okay, so there's something called let's see, that's deleting. Where is in order? So that's search. Okay, definition of binary search trees. Up here is it's a search. It's going to be called in order. So if you look at this, right? Let's take a look at this. Okay, now yeah, disregard that it's a template, right? So here, if I call this in order and I pass it my root node, okay, then what that's doing, guys, is if you look at this, right? This is you know, it's using recursion. So if I pass that root node, and if so let's say that, you know, I'm going to insert what 3, 7, and 1. Okay, and we'll put another 6 in. Okay, and so we start off with this one. We create the root. Okay, then you go with the 7. You start from the top, and it's greater than, so it's over here, right? Then you start with the 1. Well, the 1's less than a 3, so that goes over here. Then you go with the 6. Well, the 3 is greater than 6 is greater than 3, and 6 is less than 7. So that's how our tree looks. Okay. So if we call this in order, right? So let's keep track. We pass the root, right? So we pass this guy here, right? So since P does not equal null, then I'm going to call my function again. I'm going to do a recursive call, and I'm going to pass it the left link. So now this is where I am. Okay. Does P equal null? Pointer? No, it doesn't. Okay. It does not equal null. So if I'm going to call P on the left link again. Now here, this left link is a null, and this right link is a null, and so forth and so forth and so forth, right? These are all nulls. Okay, so once I'm in here, right? I'm going to do a third or a second recursion, but this time I'm going to pass it null. And here's where this guy here fails. We stop the recursion and we return back up. Now we returned after this guy here. So at this point, we're going to print the 1, right? We came out of this guy, came back from here, and we actually did a printf on this guy to print. So this guy here has been printed. We now are going to go down the right side of this guy. Well, that's another recursive call. But when I go down the right side, that's a null. So we come out and then we're done with this level. So then we, then we come back out, right? And now we are on this leg here, okay? So, we continue doing this. Now it's going to go down the right side, okay? So you've got here, you've got recursion once. So here's a level 1 recursion. Here is a level 2 recursion. Then you come back, and here's another level 2 recursion for this side. You come back, right? Then you're back to the root node, and then you've got a level 1 recursion again. And here you've got a level 2 recursion. You come back, go down this side, another level 2 recursion. You come back up. Then you're, once you return from this last one, then you're done. So what happens is that this guy dances around and outputs these. It's going to output in this order: 1, 3, 6, and 7. Okay. Now you've got one of your assignments on this is to create a dynamic linked list, but it needs to be, right? It's got to be a sorted array. So I want you guys to think, I'm kind of going to give it away to some degree, right? Let me clear my invitations here. Okay. So here you have, one of the things that you have to do is you have to, what? Okay, contents of. So this is to return a pointer to a dynamically allocated array containing the elements of that binary search tree in sorted order. Now, look, what happens if, when I call this, if I call a selection sort, right, on that array, let's say that there was 5 nodes in there, right? If I call selection sort on these guys and sort this, do you think my function is going to be big theta?
No.
No, what's it going to be?
N squared?
It's going to be n squared. So, okay, but what do you do? What do you have that, what do you have that is big theta? And honestly, somewhere in your text, it tells you that the BST itself operates in big theta at the end, right? So what did I just show you that can help you, that you can do and store that data into this array and just go through one time?
In order traversal.
Yeah.
Also have a question about that, since we're talking about it. Are we allowed to, what's it called, implement helper functions to do that for us?
To do what now?
Helper functions?
Oh, yeah. Yeah.
Yeah. Okay.
Yeah, but put your helper functions in your .h file for me, please.
Yeah. I mean, I didn't know. I already implemented that with, what's it called? Iterative solution. So
okay,
I guess that's fine too.
So yeah, just please put that in here so I don't have to go dancing around.
Yeah, of course.
Okay. All right. Thank you.
That you jump on disappears as soon as you jump off of it. So already just jumping right into it. Swick.
Is that my machine that's talking?
So not every block, but
yeah, I think so.
Like more critical.
Yeah. I've got this.
That and that.
Where's that coming
Concludes
from?
the lesson.
Where's that coming from?
Kaput. Wow,
Actually, I think it's somebody else.
There.
Oh, somebody's hot micing.
Bottom of the screen. I feel.
All right, let's see here. Let me, I'm going to mute everybody, and then you can unmute yourself. All right, or whoever was hot mic and turned it off. All right, so let's get back into this. Oh, there's this grade scope thing. Let's get back. Where was I? Okay, I was talking about this. So here, it's important, guys, right? That you understand that, this is the function that we're trying.
You're not sharing screen, Professor.
All right, thank you. So, how can I prove that function of x that, let's see here, that is greater than or equal to beta of x in this case here, right? So basically what we're looking at is g of x here, or g of n. I like to use x. I don't know, it just feels weird to put n in there. So how do I know that, f of x is always going to be lower bounded by beta of x, right? Well, now you take g of x in this case, right? G of x is really, it's big O of n, right? So then you just take x, you find some second constant here, such that if I multiply it against x, at some point, right? At some point, this guy here will always be higher than. Okay. Well, how can you do that? Well, just multiply it by 0.1, right? If that's my constant. Now, if they're going to force you, right? If you're forced into, into using integers, it's harder, right? And I'm going to confess, I don't know of a positive integer that can give me this, right? So I take the easy way out, and I always use a fraction, okay? Because it doesn't include 0, but any number on the number line between that, I'm allowed to use, which 0.1 is on there, and it's easy to do a 0.1 division or multiplication across some kind of a formula. All right, so as you guys do your runtime analysis on that, that's a big hint for you, okay? So again, if I'm using, if I'm using a divide and conquer, right, on that n order, well then I'm guaranteed that thing's going to be, lower bounded by big theta of n. Okay? Because I can find an n, I can find a constant, right? Okay, so so the important thing here is that you understand, first of all, how to do this, right? So let me pop into my share or my shell here. I'm assuming you guys can still see my code or see my screen, right?
Yep. Yes.
Yeah.
All right, so if I vi into, vst.h. Now, I haven't done all of it. I haven't done everything. And I don't know how to turn off that darn index or that darn highlighting either. So I hit some kind of key sequence earlier that that highlighted that index, and it's annoyed the heck out of me ever since. All right, come on. Well, I don't want to, whatever. I'll try to figure it out, Google it or something. But yeah, so if you need helper functions, by all means, you can add those in here, right? Now, one thing that I need you guys to know. So, for example, if I want to pass something by, let's see here. Okay, well, here is this in order, and I was actually calling this guy to, I believe I modified it to where it actually would. No, I did not. Let's see. Okay, there's that copy in order. So this is one of my helper functions that I use to work with the contents of. So I actually call this from within contents of. Now I'm not going to show you all of it, okay, but I'm going to show you the header file. So here, you know, I passed, you know, of course I passed my integer array, and I passed my index, and I have to pass it by reference. So when you pass by reference in C, you just pass it as a pointer, or in your header file, it's a pointer, right? So in your prototype, you don't put ampersand here like you do in C++, you put the asterisk. And then in your, so then when I call, where is it? Where is it? Oh, that's the insertion. You guys already saw the insertion, right? You guys already got this one. Okay, so here, when I called copy into, right, I'm passing root. You know, I created, you know, I passed root into here. Okay, so you're already given this, right, as a template, right, or as a yeah, as a template. So here, you know, what I'm doing is, you know, I'm going to create a dynamic array, a pointer to it, and I'm going to pass that pointer. This is how you, you know, well, this is how you pass an array, and it's just because that thing takes pointers, right? You want to make this a pointer, and so this is kind of how I did everything. I've actually got all of it working. The only thing I haven't done is the second min, I believe it is. But so here, notice that I'm setting pointer sub I equal to the address of index. This is how I have to pass that index by reference. Okay, or I could have just put an ampersand in front of this, but I was having some compiling issues when I just tried to pass ampersand index into here. Okay, so if you're struggling with this, right, go ahead and work on it, and you know, you guys can work on, for the most part, you guys can work on this one together, because I'm not, you know, I'm not running this guy through through grade scope. You know, I fully expect you guys to help each other. And the primary thing here is that you get accustomed to passing things by reference using this terminology here that's unique to C, okay? And that you are comfortable with malloc. You know, how do you know how much to malloc? Well, you get the size of, and since an integer is what I'm using for this index, right? I'm sorry, array size, I'm going to be storing integers in there, right? So how many integers am I going to store? Well, I'm going to get my array size is 0. Array size equals size of root. So that's one of the functions you have to, you know, and how can you do that? Right? How can you compute the size of root or the size of your tree? The same way that you can, you know, this in order, right? That in order is so useful. Okay. And look how many lines it is. Okay. All right. So questions on the binary search tree. Actually, let me, before you have any questions on it, let me run I clear, and let's just run this. So here now I believe some of this is extra code that I've added that I'm going to be taking out of my main. So let me go into my main and kind of take out some of that stuff. Let's see here, because you know, I don't want you, I mean, you can modify your main to practice and stuff, but I don't want you to I want you to revert it to its original. Okay, actually, let me do this. Because I don't know what I have, so I'm going to copy. Let's see, I'm going to go into it's in my etc. And was it classes? Goodness, what was the? Let's see. Let's pull up I'm going to recopy, and you guys will probably need to do the same thing. There it is. So I'm going to copy user class CS1D assignments A0, and I'm not going to overwrite my stuff. I just want main.c and store it here. So now then, if I clear, and am I nested? No, I'm not. All right, so now if I run make, okay, then this thing is reran. Okay, and of course, you know, you can always do a make C, or is it make, what is it? Make clean? Which one is it? Oh goodness, let's see here. If I do man make and then type in less. If I want to clean, or is it make file clean? Let's see. How was it that I cleaned before? All right, let me Google that. Because you're going to need to, or there's going to be a time that you're going to need it. How to, I don't know, make file clean. How to make file clean. Make clean. All right. Make clean. All right, so now what that's done is that's removed all my .o files. Okay. So now if I clear and then I run make, you're going to see that everything compiles cleanly. Okay. And so now if I run, okay, all right, I guess I didn't put that in there. That this is part of the actual output of how it should be. So whenever you guys take your screenshot, right, what you can do is, let's see, what can you do? You could probably actually pipe the output to a text file. Let's see here, test.txt. And then if I do a, you know, I could catalog it, or I could just, you know, go into it, do a VI of test.txt. And then here you see all this, right? Okay, so so there's my, you know, there's my tree. That's the sorted. That's here. It's actually printing the dynamic array. It doesn't have a second smallest element only because I haven't implemented that function. And then here it's going through and showing that I'm deleting my nodes. Okay, so this is how I'm telling whether or not you freed up your memory. And then of course, now it's cycling through the next file, which is balanced tree. And then it's cycling through skewed tree. Okay. And here it says, here it's going through my lots of duplicates file. And here you're seeing that it's giving errors, right? Item to be inserted is already in the tree. Okay. Duplicates are not allowed.
Professor?
Yes.
I was just looking at the output of my program, and it's only the hanging tree. It's not the rest of it.
What's that? It's only deleting what?
The hanging tree, the first one.
Yeah, that means that there's some issue somewhere with one of your, I mean, have you implemented every single function?
Yeah, and it doesn't give me any errors, or it doesn't,
Yeah,
come off.
I'll have to look at that. Maybe we can look at that during office hours.
All
Okay.
right.
So, or Cena, have you tinkered around with the main.c file at all?
Not at all. No.
Okay.
Just copy
And
it.
you, okay. Well, we'll have to take a look at it during office hours. Okay.
Okay.
Okay. So this is, I mean, as you can see, I just copied the source file back from main, right? So it's clean. It's a clean make file. It's the exact same one that you guys have. And so when this thing, it's the same machine, right? So this is another good reason why we're using one VM, the same machine for everybody. So I can kind of help Cena rule out some, some variables in trying to debug what's going on with this program. So number one, we know it's not the version of his OS. We know that it's not his compiler. We know that it's not his make file. Actually, we don't know that. But he can, he can recopy that down as well. And then we know that it's not main.c. So the problem has to reside in one of his functions with regards to, well, inside of main, Cena, you probably need to put some F or the equivalent of cout statements, some printfs inside your main to see where exactly that thing is exiting. Because when you look at,
I think the program just compiles and runs successfully, because if it doesn't, it just says abort, right?
yeah, so it's going to abort here at some point.
Yeah, it doesn't abort. That's what I'm saying.
Okay.
I think you added some things to your main.
Not this one. I just downloaded it. So if you want to try it, just re-download. Oh, that was the make file, right? No, that was main. Which one did I just copy? I just copied my make or my main, didn't I?
How many lines is your main?
Let me make sure I'm not. Let's see here. So it's 7,055 bytes. If I go into it, it looks like the main is 208 lines. Is that what you have?
Yeah, exactly.
Yeah. Okay. All right. So we'll see if we can figure it out. All right. Okay. So that is about the amount of help that I want to give you. So I want you to try to, solve them on your own. Okay. And you've got all these functions that are already written for you inside your Mallet textbook, right? I don't know that you don't need the pre-order, and you don't need post-order, and we're not going to be deleting an individual node. So I'm not even interested in covering that. Okay. Now you do need to delete everything. Now, how can you go through and delete everything? What can you use to go through and delete everything?
In order and free.
Yeah. So you get so much use out of, because what in order does it goes to the bottom to all your leaves, right? Now you don't really care which order that they're deleted, as long as you don't get lost, right? As long as you don't lose your way back up to the root. And that's what in order does. Well, actually, you don't even go back up to the root, do you? Because it's not, in this case, the root could get deleted, and most likely is going to get deleted before the rest of its leaves, right? Before the rest of its branches, which is fine, right? I mean, we're going to delete the tree and set, set the root node to null for the BST. So, we don't care, right? We don't care that it's, which order things are deleted, as long as it can find its way to every single node. And this guy right here, in order, would do that for us. Okay. If you wanted to know the height of a tree, you could, though I don't. This is not, this is not something. This is not a requirement. The only ones that you need to do are the ones that are listed here. N2, which I gave you, free the tree, right? So you can call the in order for that. The size of this returns the number of nodes. Again, all you got to do is call that in order and keep track of a count, right? So you're going to have to pass that. You're going to have to pass that count as a pointer, right? So in your prototype, for that size of, let me pull up my prototype. Let's see, where's size up? Size up, here it is. Well, you don't change this, right? So you're passing a pointer, right? But you're really passing the, actually this is going to return, right? It's going to return a value. Now, size underscore T is some type of integer, okay? I'm not quite sure what the difference between size underscore T and an int. Maybe if one of you guys knows it, you can tell me off the bat, but don't change. So these original files here, right? These original header files, you got to leave these alone with respect to the prototypes, right? Because I'm expecting everybody to have the same ones on these. Okay. You go change.
I apologize to break you, but I think I made a mistake. You cannot do an order and delete. You have to do post order and delete.
Say again. You cannot.
I think I made a mistake by saying out we can do in order and then free. We have to do post order and then free. Yeah, it's not possible.
Yeah, I actually used in order on mine.
Yeah, because after you delete it, if you want to access the right side, you would be dereferencing a memory that's not yours. See what I'm saying? Because the delete one would be in the middle of the left and right, and after you delete it, you would be dereferencing the right side, which you already deleted.
But no. See, the thing is, and I actually verified that deletes it. Let me.
It does delete it, but it may crash.
So if I have this, and then let's just make a simple one, right? Okay. So if we traverse down this guy here is null, right? We're using our in order.
Yes.
Right? So once you get back into this, right? So you've got your in order, and then you've got your free, right? So this one here goes left, this one here goes right, okay? And so when you delete this, right, you're going to free this guy up. You are, let's see, you're going down the right side, but whenever you return from this, so see, you actually, recursion one you return out of recursion 2, right, you're coming back into this guy.
Yes. And then once you do, you delete the 3, right?
Yeah, but you're free in here. But whenever you return from here, right, you're still in the level of recursion that knows where you're, that you called from here.
Yeah. So before we access the right side of the tree, before we go to the right roots, we would delete the node and then access the right. You see what I'm saying? That's how you print it. That's how you delete it, right?
Okay, but this guy right here, yeah, let me think about that. I got to think about that.
It has to be post order. So. I've made that mistake before.
Okay. Okay. All right, Cena, I'll take a look at it. You know what? If I were a betting man, I would bet you were right. And, it's kind of hard to tell. And this is where I was hoping that what was it, Valgrind?
Yeah.
let me get in here. Let's see if and I was really hoping that that Valgrind would show this for me. Okay, I'm seeing some comments here. Let's see. I see the chat blowing up with comments. Let's see what we got. Oh, you guys are just talking about other things. Okay. All right. So that's a good discussion, Stina. So you've given me some homework, because while I have a tendency to, I believe you enough to doubt myself now. Okay. So let me take a look. Yeah. Let me take a look and I mean, here's my output. So here I'm deleting it. 4, 5.
If I may, can you bring up an order code that we just?
Yeah, sure. Oh, that's the same. Yeah, that's the same code as we have in your textbook. I don't mind doing that. All right. Everybody, yeah, yeah. Go, Cena, go.
So that in order.
Look at that.
Yeah, so what we would be doing is that we would delete it and then we would just say p.write, which we would be dereferencing a memory that's not ours.
Where is my 3? Let's see my 3. Hold on a second.
Free tree right there. Yeah, you see you're doing a post order.
Ah, you're right. You're right. All right. So you're right. You're right.
Yeah.
All right, guys, let me quit giving away. But you're right.
Yeah, I mean, I said it out wrong the first time, so I just wanted to point
well, it's one of those things where I did it, and I did not. Well, actually, let's see. Did I pull that out of our textbook for deleting? I probably did. Let's see. Is that in here? Let's take a look. Well, I know it's in here. So what I did when I just basically went to the Malik textbook here, and let's find delete. Well, that's delete node. If you're going to delete from a tree, okay, come on, keep going. So I believe this is a little bit different than mine. Mine was a lot simpler.
Yeah, that's deleting a node, right?
Okay. Yes, delete tree. Let's see here. Delete from tree. Let's go down a little bit farther here. Delete node. Did I just get lucky? Delete node calls my.
How is it two delete functions? Delete node and delete from tree.
So what they have is, let's take a look at the comments here. Delete item from the binary search tree. If a node with the same info as delete item is found, it is deleted from the binary. Here you're, okay, this one is trying to delete a target. You're giving it some sort of identifier, right? As far as I understand it. Yeah, this one it's looking for a particular node to delete.
That's a value, that's a pointer. The delete from tree, it's a pointer. Okay. Cool.
And so the second one, delete from tree, function to delete the node to which P points. So this one finds it, and I guess it calls delete it from the tree. But where is the one for, there's one in here for freeing up the whole thing. Oh, there it is.
Destroy.
So folks, that's what page is that? That's page number, okay, that's page number 1365. Okay, so this is, yeah, this is where I got it from. Okay, so guys, all you got to do is, you know, take a look at chapter 19. You know, I know this is kind of new, but, you know, we've, you know, you're going to have had 3 weeks total, right, to, or like 2.5 weeks to have done this. So I'm fairly comfortable that you guys can pick this up. Has anybody else gotten it mostly done besides Cena? No, is Cena the only one that's pretty close to having it done? Okay, I'll take that as an affirmative. Okay. All right, guys. So today's January 26th. Let's get hot on it. I've given you a vast majority of the code. Okay, some of it unintentionally, like just now, but you are allowed to help each other on this particular assignment. Okay. Now for the BST. Now for the other one, no. Right. So let's talk about it, and then we're going to take a break. When we come back, we'll use the remaining time, which we don't have a lot, to get into this RNQ, which I am going to release that assignment next week. Okay. So, all right, let me share my screen again. Okay, now this is the one that you've got to think about. Okay. So for this cities, right? So let's see here. So design an algorithm, okay, that given a list of n cities, okay, and some number k, return a list of that many cities that are the closest to you, right? Sorted by increasing order to distance. Now, your algorithm should run in big O of n plus k log of k time, okay? The improve your algorithm meets the required time bounds, right? So what sort of search algorithm do we have that runs in any kind of a log?
Quicksort? Like
What is
n log n?
Yes. Okay. And there are other sorting, or I'm sorry, searching algorithms, right? Now here it's talking about, this is talking about finding, right, the 10 cities that are the closest to you, and turning that list back to you, right? Sorting the list in its sorted order. So the assumption here is, now don't write your code. See if you were quick, and if I didn't catch this, what you could do is pre-sort the algorithm, pre-sort the data structure, right? Which we are going to get into. That is an approach, by the way, but that's an approach that I'm not going to allow you to do this time. Okay, which is pre-sort the data and then just grab the first K, right? So, I want you to think about it. I don't want to, other than what you're seeing here, I want you to think, okay? And some specific details, you can assume that no two cities are the same distance from you. Now look, what have you guys studied so far? What's the only data structure we've studied so far, right? What's the assumption on the binary search tree? What's the assumption? Yeah,
It's all them.
Well, you can't have what? Duplicates, right? You can't have duplicates. So here they're saying that you can assume for simplicity that no two cities are the same distance from you. Okay, notice what we're talking about here. Okay, now you can, there's nothing saying that that your node, if I mean, you may not even want to use a BST, right? But the data in here, there's nothing saying that it can't be a struct, right? Okay. There's nothing saying, that this node has to be a primitive data type. It can be a more advanced data type. Okay.
Professor, help me
Yes.
understand this. Is this supposed to be a graph-like problem?
It is. It's kind of like the traveling salesman.
Yeah, exactly.
Yeah.
So
Yeah.
it
So
is a
it's so let's say that I have my city. This is me, right? And let's say that this is city number 2, right? And so the assumption is that this distance, right, that no two cities are the same distance from you, right? So maybe there's another one over here, a little bit closer. Maybe there's one over here, okay? But the distance actually, let me erase that. I'm doing a critical path. I don't want to do that. Let's say, and here's another one and these are all straight line distances. That's what this second part means, okay? We mean Euclidean distance. You can look that up, okay? So you're going to have to compute the distance, right? Now, it may be that, let's see here. We're already assuming the world is flat. So while we're at it, it seems pretty reasonable. Also ignore things like roads and speed limits. As a hint, think about algorithms you studied. Well, not just the CS1B now, the ones that we studied so far in 1D, and see if any of them would make good for subroutines. To make things easier, right? These are the 3 things that I want you to talk about, right? And honestly, this one is worth half the value of this assignment, which is this part's 25 points, right? The other one, the BST, is 25 points. This one is the only one that you have to do this kind of discussion for me with, right? So you're going to have to upload, or you're going to type these into fields, into Gradescope, and then your code, you're going to have to upload that into Gradescope as well. And then, the screenshot, the little picture, goes into Canvas, right? And those directions are inside your assignment, okay? So this guy here, do we give any it could be, let's see here. Let's read toward the bottom here. A note on this problem and other problems going forward: when measuring runtime in the context of algorithm data structure, it's important to distinguish between deterministic and randomized algorithms. There's a lot of research into how to take randomized algorithms with a nice expected runtime and convert them into deterministic. We haven't covered any of this. So all this is saying is that there's a harder way to, there's an easy way to do this and a harder way to do it. And what I'm noticing is, let's see here, let's imagine that you have a list of all the cities in your area. Each city is tagged with its location, which you can imagine is a point in the 2D plane. Okay, so what's my data type? I'm going to have,
an X and Y.
X and Y, right? Do you want to put a name in there as well? So maybe you have a string for the name. That would be nice, but it doesn't tell you, right? It tells you just, the only input and output, or the only input is K. Right? So you're going to input the distance, and it's going to output in cities, right? It's possible to end 0. Okay. And so here you have, an integer for X and an integer for Y. I mean, if I were you, I'd just put that into a struct and then have that as my individual piece of information, right? Now, if you want to put that into a regular array, if you want to put that into a linked list, if you want to put that into a binary search tree, then have at it. But you got to keep this in mind. So that's going to rule out some of those options I just gave you. Okay. Because you also have to sort. And remember, with an algorithm A, if I have function 1 that's based off of n, right? Then I have another function in here that's n squared. Well, which one of these determines my overall worst case runtime? It's the n squared one. So if I have a selection sort in there, then I'm wrong, right? Because that's going to violate this. Okay. All right. It's 5:03. I'm going to take a 5-minute break. We'll come back and we're going to get into range minimum queries. Finally going to get into it. Okay. So I will see you guys in 5. Okay, guys, let's go ahead and let's resume. So here, what we have is a discussion, right? We're going to start, let me get to my modules page here. Okay, so we're now beginning our section for pre-processing versus runtime trade-offs. Okay, so range minimum queries is a part of that. Now, the way that range minimum works, right, is you're going to give two indices, and so basically you've got an unsorted array, right? And if I give this index here and this index here, right? Where is the minimum value within this range? Well, you can look at it and see that it's here, but how are you going to compute that, right? How do you figure that out? Well, there's really, because it's not sorted, one way to do it is just do a brute force sequential, looking to see what the minimum is and just doing those kind of comparisons. Okay, so that's what that's the functionality, right, of range minimum queries. That's how the query works. Okay, let's see here. Okay, so here's an example, right? And this should look familiar here. You've got a series of elements in some sort of data structure, most likely an array, and you're asked to find the range minimum between two indices, and here we find it. Okay, but how do you find that, right? You've got to go through and compare each one and return that index. Okay. Here's another example. Okay, and again, you take the entire block and you have to go through and compare every single one of these because this is not sorted, right? The assumption is that it's an unsorted list. Okay, and here you can even have both indices I and j equal to the same value, right? It's still the same algorithm, right? For notation purposes, we'll denote a range minimum query in array A between indices I and j as the following. So that's the notation that we're going to get used to for this. And for simplicity, let's assume that we have zero-based indexing, okay, for our arrays. Okay, so we can come up with a trivial solution. There's a simple big O of n time algorithm for evaluating RMQ. This basically just that's what I said earlier. You're just going to iterate across, that range and find the minimum. Well, that's just a linear or big O of n, right? You're going to compare n elements one time. So that's pretty trivial. Okay, so why is it, we're asking here, why is this problem at all algorithmically interesting? Okay, well, it's interesting because let's say that array A is fixed in advance, okay, and you're told that we're going to make multiple queries on it, right? So, that array is not going to change. Then can we do better than big O of n, right? Do we have to search through every single, through the worst case would be that the indices are at the beginning and to the very end. Would you need to search that every single time? Or do we want to do that every single time there's a query? If that data doesn't change, right? And if you're going to do 1 million queries in a day, that can actually start to eat up on some processor time, right? So can we do better than that? Well, the answer is yes. Okay. Otherwise, we wouldn't be talking about it, right? So So here in an array of length n, there are only big O of theta n squared possible distinct queries. Okay. And so here, this just kind of gives you the reason why, kind of walks, pardon me, as my mouse is jumping around here. You know, so first you could have one subarray of length 5. So maybe you scan the entire piece, right? Or maybe you have 2 subarrays of length 4. Maybe you have 3 subarrays of length 3, and so forth and so forth. Now again, here we only have like 5 items, right? Well, in this case, the assumption is the array is 5. So, you know, the only possible combination is 0 and 4 on this one. Here, if the length of the arrays are length 4, you only have 2 possible combinations, and so forth and so forth and so forth. Okay. So there are only big theta of n squared possible RMQs, right, in an array of length n. If we pre-compute all of them, right, we do that one-time computation, then we can answer RMQ in time big O of 1 per query, right? So let's see here. What's the example he's got? So let's say that this is our array, right? 16, 18, 33, and 98. And these are my indices, okay? So if we do the computation, right, let's say that, let's see, we're going to compute index of length 3. So if we have, if the indices, if the beginning is 1 and the end is 3, then what's my minimum? It's an 18, right? You guys see that? You see what we're doing? Okay. So, so again, this is, I mean, that's the equivalent to 4, right? But we're using, it's a, the indices are from 0 to 3, right? And so this guy here, let me move my little window out of the way. That's going to be an 18. Now then, so one simple approach for this, now that was an example, okay? So one simple approach is for each entry in the table, iterate over the range in question and find the minimum value, okay? And let me just finish this slide here, then we'll stop and pick up next class. One simple, let's see here, how efficient is this? Well, the number of entries is big theta of n squared. Time to evaluate each entry is big O of n. Time required is big O of n cubed. Okay, the runtime of big O n cubed using this approach. Okay, it is also, is it also big omega of n cubed, right? So here's the example. So we go through and we're running through these. Okay, we build this table, right? And each entry in yellow requires at least n over 2 big O of n, right? That equals big O of n work to evaluate. So we go through this problem. There are roughly n squared divided by 8 entries here. Okay, so if let's say that n is 8, what's 8 squared? 8 squared is what, 64? Divide that
65.
divide that by 8. So there are 8 entries here. Total work is going to be big O of n, or a big theta of n cubed. Okay. So here, that's if you, do that, do the big, if you go through this thing every single time using loops, right? So here, a different approach, right? Naively, pre-computing the table is inefficient. Can we do better, right? So let's stop here because we're already 2 minutes over, right? But as you guys can scan through this, you'll see that as we're doing this little cross matrix here, it's easier if you look at these, right? So if I'm only comparing 0 and 0 and 1 and 1 and 2 and 2, right? I've gone through here. Now then we just go one more time and we're going to compare from indices 0 to 1, right? We compute that and so forth, right? So you can see that this ends up being an n squared big theta of n squared. Okay. All right, now there's more than this, right? So anyways, what I'd like for you to do is, well, first of all, work on your binary search tree, right? Because those problems, well, that and the find the cities, those are the kind of questions you're going to be asked on your exam, right? Your exams are going to be essay type questions. And so these handouts, right? These are the ones that are going to prepare you for that exam. Okay. All right. So that's it for today, guys. My office hour starts here in about 7 minutes.
Professor, could I ask you something really quick?
You can.
For the exams, you said we had to use latex?
If you're going to, if you are going to put any kind of formulas and stuff, yes, I want you to use latex.
Okay, good.
Or latex. I guess that's how you pronounce it, right? Latex.
Yeah, I'm not sure how to pronounce it either.
Okay. I've heard it, well, I've heard it called latex. Okay. All right. So, just curious looking here. Block-based approach. Okay. All right. So we'll take a look at this, and we'll probably spend the majority of next class going over RMQs. Okay. All right, guys. I'll see you if you need office hours or you're struggling with this assignment, this binary search tree. You guys can come see me for office hours here in a few minutes. Okay. All right.
Thank you.
Okay, guys, how we doing? How we doing with the binary search tree assignment? How are we doing with dealing with C in the command line?
Professor, I have a slightly different issue. Different question. So when I try to SSH in, I can get into the system, but when I try listing, nothing shows up.
Can you share your screen? Let me see what you're doing.
ls-a. There isn't anything in your home directory by default.
Yeah, you heard it, right?
Yeah,
so
yeah.
If you do -a, it will show hidden files as well, and you should see a directory called period and another one with 2 periods.
So is it ls? Is it one? Is there any spaces in between all of that?
-a.
Okay, I get bash history, bash logout, bash profile. Oh, config, Mozilla.
Right. So you're going to need to make an A0 directory, or just do a hard copy. What you're seeing there in the handout.
Yeah, so it's the CP -RP/user that thing.
It's not -RP.
I pasted it into the chat. The command cp-r with the directories. And what that's going to do is go to the copy in the folder that Dr. Barnett provided and copy all those files into your home directory so you can use them.
Okay. Where did you post that?
It is in the chat. I'm going to paste it again.
How are you doing, Professor?
Oh, I'm doing good. Hi.
I'm
doing good.
Okay. Can we jump on my code or?
Yeah. Yeah.
Okay.
Let's see what you got.
There we go. I see it. Thank you so much.
All right. So when I do, oops, run test.
Yeah. You just get the.
Yeah.
No, it's doing them all. It's going through all the files.
Oh, is it?
Yeah. Look.
Oh yeah, you're right. But why was your output so much larger than mine? Okay, yeah, you're right.
Mine was telling it that it was deleting and everything. So
Oh.
So have you recopied that main file lately?
Yeah, I let me do it one more time. CP, where was it? It was in there, assignments.
You want to be sure only to copy that file over. If you just copy the whole folder, it'll overwrite everything.
Yeah, you don't want to do that. You don't want to do that.
Sure of that. Where's the folder again?
It's going to be /user.
Okay. Right here.
Yeah, just
CP,
user. Just class CS1D assignments. You can hit tab. There you go. A0
and then main.
Yeah, there you go.
Dot.
And then just
and then make clean. And then make.
Just make
Yeah.
So you know what? Could it be that it's probably the case? Let me check mine. I think that because I thought that I had it printing out that deleting nodes, and I didn't see it when I was scanning through it. So that made me think it was in the main. So what I'm thinking is that the reason you saw that extra stuff is that somewhere in my bst.c file, let's see, to do a search, is it /delete? Is that right? Yeah. So Cena.
Yes.
That deleting node was in my free tree.
Oh, so we're not supposed to have it, right?
No. That was in my free tree. That was just so I knew that I'm in there freeing. So if I go and if I share my screen now, if I remake, let's see, let me get in here. And so I thought that was the case. And sometimes when I'm rushing through the lectures or something and demoing, I overlook stuff. So if I go ahead and make clean here, how much clean, and then if I call run test or make. All right, so it looks like, you know what? I copied this code. See, this is part of my insert, right? And I kind of, for me, actually, I kind of, though it's not part of the requirements, I like seeing that.
Yeah, maybe two of it, like a couple of it.
Well, I mean, I guess you can't really control it, right?
I haven't really taken a look at the main code. I don't know what it's like. So
yeah. So look, some of this extra stuff you don't have to do this, right? That's I believe that was code that when I was writing this, I was, Malik is my buddy now. Okay, so Malik, I remember doing this, my God, back in '88. So this is bringing back so many memories for me. But if I do a yeah, so you see here, so I actually copied this code straight out of Malik. So that's why you're seeing that extra output.
I see. Okay.
Now you don't, right? That's not a requirement. And right. So I'm assuming that if your delete does not work correctly, I mean, I guess you could fake the funk on the delete and the output might not show it. And that's where I was really hoping that Valgrind was supposed to show me, right? And I don't quite.
I mean the delete in the tree was working fine, right? It was supposed
Oh yeah. For mine, it works fine. But earlier on, I didn't have my delete function working, and it wasn't showing. It wasn't showing me.
I mean, I guess Valgrind isn't as good as they say it is.
Well, or it's user error, and I'd be willing to bet on user error.
That too.
Okay, so all heat blocks were freed. Well, yeah, everything gets freed at when your process ends, I suppose, right? So let me do some Google searches here. All right, does anybody have any other questions while I'm kind of checking up on Valgrind here?
I don't have a question, but I just about our previous discussion in the class about the address space in the Windows, where we were talking about why it was 6 bytes, not 8 bytes. Remember? Yeah, I found something on the Microsoft website. I just sent it to you. I thought you might want to look at it.
Yeah, sure. Yeah. All right, let's see. Somebody's asking, why doesn't Valgrind detect a memory leak in my test program? So here I create a new integer, P is I, we come back. Right, and so here he's just he's running this thing a bunch of times. He says, I compile with no optimizations. Then link as follows. I run the executable and boom, right? So the reason this happened is that the call was actually running Valgrind on user bin test, which is built in a program that checks file types and compares values. All I needed was this. Oh, okay. All right, I'm still not getting it. Well, actually, mine is actually deleting it.
Yeah.
Okay, so so if I go in and well, I don't want to mess with my code too much. Let's see.
You can just make the post order an in order, and it would be just one line of code. Yeah, just put that in the middle, maybe.
Or just comment out.
Yeah, that too. I mean, you have to call the node right in order to get a, what's it called? An error.
So if I yank this and then put it here, and then comment this one out, right? So will that do it?
I don't think so. No.
No.
No. You have to put you just get rid of the right, maybe. Only left.
Yeah, that's okay.
I think that should do it.
Yeah, there it is.
Yay.
All right. All right, let's get back in here and fix this. We can't have that going on. I think that that did not change it. Yeah, I did. All right. Hey, yay! Thank you, Stack Overflow and Cena.
I didn't do anything.
Okay.
I sent you the link in the chat. It's Microsoft.
Let me click on it and see what we got here. Now I know somebody was in here for CS1B, and let's see here. I think it's Hong, or is it Johnny? Is in here. Okay, I'll have to take a look at this because I think somebody was in here for CS1B. Let me see if he's still here. Okay, Hung, are you there? And it's either Mark or Johnny. I beg your pardon for forgetting which one. And by the way, I guess, Felix, if you want to stop recording, because we're into office hours now. So I'm going to stop. Hello, Felix. Can you? I'm afraid if I force you to stop recording that it's going to ruin it. So can somebody ping Felix? Okay. Okay, Hung, how about this? How about I create a breakout room for you?
Me?
Yeah, because you had a question for CS1B, right?
Yeah.
I mean, Felix is recording his session, so if it's something you don't want recorded, then I can make a breakout room and you and I go into it.
No, it's just about like the command prompt of the serendipity.
Yeah. Okay. What's your question?
Oh, so I watched videos, but it only taught me how to navigate the command prompts. I don't really know what you want us to do on the command prompt for the.
Oh, you're just going to run your code. So you're going to go to the command prompt, go into the directory where your executable is, and just type out your executable name, right? So let me show you. Okay. So let's say I want to go into my serendipity, which I'll find an older version here. I don't have anything in here. Okay, here's one. Now this is an older one, right? Or this is one that's so I'm actually going to cheat a little bit here. You see what I'm doing and how I'm highlighting where that directory is? And
yeah.
See in here I've got, here's an application. That's my executable. Okay.
Oh.
Right. So I've already built this. Now I'm going to show you how to build it. Okay. Here in a moment to rebuild it. So now then, if I pull up my command line interface, right? I'm going to do a change directory with my mouse. If I right click, it's just going to paste that in there, right? You see what I did?
Yeah.
Instead of just manually going to G and then, this just makes it a lot easier. Now, if you notice, it still says I'm in C colon. So, but if I type G colon, I've now switched over to that drive. Okay. Now, if I do a directory listing, there's all those files. So what I want you to do is just run serendipity. Just type in, after you've compiled it. Right?
Oh.
And so here mine's running. It's kind of slow because McAfee's scanning it, making sure that it's not a virus. So you have to give it a moment. Okay. Now yours is not going to be linked to the navigation. Okay. Yours is going to take an input, and it doesn't matter if you typed in pizza. Okay. And it's just going to quit. It's not going to do any test. There is no if statement there. There is no do while loop. All you're going to do is type some number, and you're going to return. And then it's going to, right now for you, you're going to have to type in like main menu.exe.
Oh, it's a CPP file. So do I put .cpp instead?
So what you're going to do is you're going to do G. So first you got to compile it, remember? And you're going to need to name it something different than a.exe. Now, are you on a PC or a Mac?
I'm on a window.
Windows, right? PC. Okay. So you're going to type in -o main. Is it main menu? I believe it is.
Yeah, main.
So that now I don't have. Let me see. I don't have a main menu.cpp in here. Okay. I don't have, right. But if I did, then actually, hold on a second. I need to put the name of my executable. So this, instead of it being the default a.exe, that -o is going to rename my executable main menu. And then it's going to try to compile that main menu.cpp file that doesn't exist in my file. Okay. I actually, you know what? I think it does. It is in, but see, so actually it is in here. And notice that, let's see here. Oh, there it is.
Yeah.
All right. So, but see, mine is tied together. So I got to do a little bit more than just this, right? You don't have to, right? So for me, what I can do is, in order to finish things up there, I just include all my .o files. Now you're not ready for that, okay?
Okay.
But if I were to run main menu, you'll see that I get the same thing as when I ran Serendipity, okay? But you're going to do this for each of those 5 files, right? So because each of those are independent, they're not looking at each other. They're completely independent. Does that make sense?
Yeah, like 5 different applications. Which leads to my next question. How do you create the application? I can only create mine of like CPP files from Eclipse.
Oh, well, I mean, that's fine. You can create it from Eclipse if that's what you're comfortable with. But for me, I just create, the source file. I just, I like Notepad++ because it gives me colors. But you can use Notepad. You just got to say, it's got to be a, you can't have like embedded hidden symbols. Like, so if you try to use Word's going to put some special characters in there that the compiler is going to freak out over. Okay. But see, I just use, look here, I just use, let's see, here's a main.cpp. I just use Notepad++. And then, here when I select a language, it just picks a color code. I can tell it to use Fortran, right? So here, you just kind of, all it does is change the colors, right? So these are typical colors for C++, okay? It just highlights in blue keywords, right, in C++. And that right there is, I mean, it's slightly off because your header file is supposed to have a little bit more than just the word serendipity, but that right there is, minus your style sheet is how I want you guys, to answer main menu.cpp.
So I'm trying what you try to do in my command prompts.
Let me, can you go ahead and share your screen? Let me see what you're doing.
Oh, not much. It's just, dang it, not here. Oh,
yeah.
Screen share. I'm gonna screen share my desktop because that's where my workspace is.
Sure. Yeah. And George, Hung here. Is it Hung? Is it Johnny or Mark that you go by?
It's Johnny.
Johnny. So yeah, Johnny's actually in my 1B class, so he's not on the private server. So okay, Johnny. So do a dir. Let me see the files in your directory. Just type in dir. And okay, there you go. So do this for me. Type in G++.
G++.
Yes. -o.
-o.
Space main menu. Space main menu.cpp. Okay, so you have it installed MinGW.
I have.
Okay, well then you haven't stored it in your environment variable. So what you're going to have to do, go ahead and close down, kill out this prompt, okay, and go ahead and share your screen again.
Okay.
And I want I want to show you what to do. And we can do this in about 2 minutes.
Okay.
If you've already installed it, I want you to open up your Windows File Explorer, the little manila envelope, and navigate to where you installed that. That's probably C:\program files min.gw. Can you?
Let me. Yeah, here's my file. Let me try to search it. Min.gw.
You're not sharing. Yeah, you're not sharing the right window.
Huh?
It's a blank screen. So you got to share the exact window that you're using.
Oh, let me see.
Yeah,
Share again.
stop sharing and restart.
There we go. Share this one.
Yeah. So click on this PC.
This PC. Oh, okay.
And then C:, your C drive.
My C drive. You mean?
Yep, that one right there. And then go to Program Files. Oh, wait. Go back. I saw it.
Oh, okay.
Yeah, right there it is. min.gw. You see min.gw?
There it is.
Okay, click in there and then go into the bin directory. And I want you to look down and see if you find G++ in there.
I can search it out.
Yeah, I know you will. Go ahead and look. It's in there. Yeah, it's in there. G++.
Oh, here it is. This one?
Yeah. So now I need you to get rid of that search, whatever you just did, because you kind of messed us up.
Okay.
So go ahead and click the X button to close the search, to close out the search. Yeah. So now you see in your little address bar up there, I want you to click inside your address bar. Higher, a little bit higher, a little bit higher, a little bit higher, right there. Now go back down. Go inside at the right, but don't click. Yeah, click to the right of bin. Click to the right of it. Click
to the right of bin.
Yeah, just click in there, right there. Copy that.
Okay. Control C.
Right now, go down to your Windows icon and type in the search. Type in env, and you're going to see environment variables or something like that. Can you do that?
Can you repeat that?
So go down to the bottom where your Windows icon is in the search bar. So you can go ahead and close out of that. We don't need that anymore.
Okay, so I'm in the search bar.
Okay, and then type in the letters env, the beginning of the word environment variables.
ENV?
Yeah. Yes. Like
ENV.
Yes, env, environment.
Yeah. Edit the system environment variables.
Okay, can you share that? I can't see it.
Okay, new share. I don't think it allowed me.
Okay, can you just close out of that window right there? Or close out of that. We don't need it anymore. And share again and just share your entire screen. You should be able to share your entire screen.
Oh, yeah, here it is.
I mean, as long as you don't have anything personal on there.
Yeah.
Okay, so there you go. Type in env. I can see it now. Edit system environment.
Open.
Sure. And then environment variables, bottom.
Bottom, there we go.
Yep. And then go down at the bottom where you see path.
Path?
No, you passed it up. You went too far down.
There it is. Path.
Right. Click on edit.
Edit.
Then click on new.
New.
Oh, you actually already have it, but go ahead and click new.
New? Okay.
Yes. And hit paste.
Paste.
See, now I see, it looks like you've already tried to do this once before. So where did that, if you look 2 lines up, where did that come from?
I don't really know.
Okay, that normally doesn't, somebody normally does that manually. That's interesting. Now, go ahead and click on OK.
Okay, the new one that I just added.
Yep. And click on OK again. Click on OK again, and then reopen up your command prompt and go to that same directory where your folder was. So
Right
you may have to.
OneDrive. So.
And you can hit tab to auto complete those if you don't feel like typing it all out.
Oh.
You can just type in a couple of letters.
Ah, dang it! I reset everything. You know.
So
OneDrive, desktop.
So hit tab.
Oh, tab.
Well, that's fine. No, just go ahead.
Workspace and then
just type it the hard way. That's fine.
there we go. There we go. I'm in that serendipity file.
Now do a DIR listing.
dir, yeah.
Yes. All right, now then go ahead and do that G++ -O main menu blank main menu CPP.
Main menu dot cpp.
Yep. Hit enter.
Yeah, I did enter. It's gonna take some time. Like,
There
wait.
it is. There you go. Now type dir again.
dir.
And you see an executable in there?
Yeah, main menu dot.
Go ahead and type in the word main menu. You don't even need to put .exe on it. Type in main menu.
Just main menu?
Yep. And that's going to run that code. There you go. Now, I'm going to get on to you because you're not clearing the screen. You see how all that other junk is up there?
Yeah.
Above the serendipity program. So I want you to clear the screen the very first line of code inside your int main.
Yeah, CLS, right?
Yeah, yes, system CLS inside the string and parentheses. Okay. So was it that wasn't that hard, was it?
Yeah, I just needed to,
Right. Now tomorrow's going to be a train wreck, right?
Yeah.
It's going to be a train wreck. So I need you to be a witness that it's not that hard. I guarantee you some people are probably stressing out already.
Yeah.
Okay. Yeah, it's not that hard once you get used to it.
Once I exit out the command prompt, do I have to create another executable?
Yeah. So you'll need to create an executable for each of those pieces of program that you're working on.
No, I'm talking about like each time I go back to the command prompt, do I have to redo them or are they?
No. That executable, you can. So if you were to, close out that command prompt and come and navigate back in here, you can always run that executable.
Oh, let me see. Oh, there it is. It's there.
Now,
yeah.
Sometimes on my system, I've noticed that I can't run it from the navigator, but go ahead and double click on that and see if because it may run and just, okay, but if you type something, it'll close the window down when it returns. So go ahead and type something, hit enter.
Cool.
See, it closes the window. And a lot of times we don't want it to close because I want to have a chance to read your output, right? Before it disappears. But, so here, see, that's inside your Eclipse workspace, right? So you can write your code inside of Eclipse if you want. I just need you to run it from the command line.
Okay. Thank you.
Dr. Barnett.
Yes.
I just had a quick question on the cashier.cpp. You just want us to output everything, right? You don't want us to manually enter it through the terminal?
No, you do. Yeah, you do need to manually enter your inputs from the command line.
Oh, okay.
So,
can I show you what I have so far, if that's okay?
Sure can. Go ahead and see, Johnny, go ahead and stop sharing and let
Sure. But what are we turning in for the assignment? Like all the CPP file? Like, do you want this?
Right. You're going to upload all the CPP files. But but I'm not going to grade from your submission. The reason you're going to put it in Canvas is just for historical purposes. I'm going to grade you based on what you demo. So I'm going to have you show me your code a little bit. I'm going to look at you executing your stuff. Okay. Felix, are you around? He's gonna eat up his hard drive here with this file.
Professor, I'm just gonna go ahead and log off. So
okay, all right.
We can talk about that virtual address space later.
Sure. All right.
Thank you for your
have a good day.
Have a nice day.
Okay,
Can I share my screen?
Sure, go ahead.
Okay. Can you see it now?
I can.
You can?
So go ahead, go ahead and take me to your directory where your code is.
Okay.
Now you can hit tab as you're spelling it out partially, and it'll complete that word, right?
Oh, okay. All right. So
that way you're not hit tab.
All right, that's okay.
And then put a slash after it. So
slash.
Well, go ahead now. What's the next step after desktop? CD what? Now don't hit enter to hit tab. Hit V space whatever it is.
Yeah,
and then
this one.
put a backslash above the enter.
Okay.
Above the enter key. Okay. Now what's the next directory?
Well, I'm supposed to enter this and then dir.
No. You didn't have to enter it. You can actually type it all on one line. Not have
Oh, okay.
That's what I'm trying to show you. But maybe, I guess it's there, right? That's where it is.
Right. Okay.
All right, so let's see your cashier.
Oh wait, whoops.
Okay,
This is the, sorry. No, yeah, this is the code. Let me okay. Cache. Yeah. this one. Okay, I just wanted to make sure. Does it have to be like this?
Well, yes, but a little bit of a tweak. I want that 239. I want you to right align that underneath the 9 to be underneath the 0. You see that?
Oh, where? I'm sorry.
Yeah, look at the tax result.
Okay. The tax, all right.
But look at the result.
Yeah, 239.
So I want the 9 to line up with the pennies on the other figures.
Oh, okay. I see what you mean. But I just wanted to make sure it has to be like this, right?
So that's correct for the second part, but the first part you're going to be reading input from the command line. So you're going to prompt the user. So if you look at that PDF, it tells you exactly what you're going to be typing in.
Okay.
So you're going to have to get line and cin and all that jazz.
Oh, okay, I see. All right.
Okay. And
so it's so for this we do the get line and cin, and then it's for the book info too, right?
No, we're not. Yeah, book info has nothing to do with this.
Okay.
Okay, so all you're going to do here is take what the user has entered, and you're going to print out the data, print out the variables, do the computations, and print out the results. Now that's going to be the result, what you have there. But what I'm going to want you to do is store that data in a text file that you have handy.
Okay.
That way you can copy and paste that data and not have to hand type history of Scotland.
Oh, okay. I see what you mean. All right.
Yeah.
Okay. So I'm supposed to manually enter the ISBN, the quantity, the title, the price. Okay.
And then after you've entered that last piece of data, which is the price, when you hit enter, it should clear the screen and then print this exactly what you got here, but using your variables, right? I don't want you.
Okay.
Yeah.
Okay, I see what you mean. All right. And then like for the rest, it's just outputting. It's just outputting, right?
Yeah, and the purpose of this right now is just to test that you've got the computations working correctly.
Okay.
So we just put in some trivial data in there just to verify that your receipt is correctly computing the subtotal, tax, and total. And so that's why everybody's using the same piece of data, is so that you know what the correct answer is.
Okay. So you said so you said after I input all of these values in up until the price of the screen is supposed to clear.
Yes. Yeah. So clear the screen so that all that I'm seeing is a receipt.
So how would I that would be a system CLS or?
Correct. Yes. So after you've done after you've gotten the data and maybe you've computed your values and your variables, then do a system clear CLS.
Okay. But how would I actually do that on the command prompt? It's itself like just
no, it's code. So inside your code, you're going to put the word system blank and then open and close parentheses, and then inside there you'll put the string CLS.
Okay. All right.
So it's actually a piece of code that you put in there.
Okay. And it's just supposed to output this stuff. Okay.
Right.
And then I just had one more question.
Sure.
Just the.
And look, I know tomorrow's going to be a train wreck, so
yeah.
It's you're actually already. So it looks like you already have it.
Yeah. So and then for this one, the book info, we just manually well, I mean, like you said, we create a separate text file and we just copy and paste. Is that what you want?
Yeah, but is that, I don't recall the date and all that being a part of that. So yeah, so let me finish.
Okay.
All that book info does is output the that text that you see in the PDF. There is no data. You're not entering data. I mean, it's that simple. It's just like a list of like 7 C out statements. That's it.
Oh, okay. So like I can just I don't need so for this one, for the book info, I don't need to manually input in the data. It's just for the okay.
That's just ready for about 3 assignments down the road when we actually call it. and
okay.
you're going to be passing data to it. Right now, it's just a stub function. It's just sitting there, and I'm not even going to look at it.
Oh, okay. So I pretty much input nothing. The data's already supposed to be like
Correct.
In the actual code. Okay.
So so if I were to have you compile it and run it, right? I mean, I may change my mind. I may have you run it. What's going to happen is you're just going to clear the screen in your code. Your code clears the screen, and it just outputs those 7 or 8 things with no data assigned to them. Just the titles of the, what you see exactly on the PDF of book info.
Oh, okay. So no titles. Because I was checking the PDF 3. It did have titles. It had like a date, an ISBN number.
Let's see
So
here.
I was just wondering.
Hold on a second. So let me just double check that. And I'm going to share my screen here. Hold on.
Okay.
Yeah, let's see here. Let's get in here. Let me share my screen.
Okay.
Is that chapter 3?
I believe so. Yes.
Actually, no. I think book info is chapter 2.
Okay.
Let's see. Yeah, this is it right there. That's it. This is
Okay,
all you're outputting. There's nothing in there.
Oh, okay. Because I was just asking because in the third PDF, yeah, it had like like an ISBN, a title, a date, and stuff too.
Oh, but that's not. Let's see. Let me check that one.
Okay. Yeah. Below.
Yeah. Let's see here. Well, wait a minute. Whoa. This is not book info. This is the input for cashier module.
Oh, okay. Okay.
So you're going to output date, and you're going to let the user type in this string.
Mhm.
And then after they enter that, you're going to prompt them with this prompt, and then they're going to type in a 2. And then you're going to prompt them with this one, and so forth and so forth. And then after you hit the price in here, after you hand type the price, right? You're going to clear the screen, do all the computation, clear the screen, and then print this nice looking receipt.
Oh, okay. I see now. All right.
Yeah.
Yeah, that's all I had to ask. Thank you very much, Dr. Barnett.
Okay, you're most welcome. You're
Thank
most
you.
welcome.
Wait, we need user defined file like ifstream.
No. I want you to enter this stuff by hand. But the best way to do this, what I also want you to do, right? So you're going to read the data from the user. The user's going to be typing this data in. I don't want you doing file input. You're making it harder than you need, Johnny.
Oh, okay, yeah.
Okay. So what I need you to demonstrate though is the ability. Let me find it. It's somewhere in here. Okay. You see here how I've already typed this data here in this text file? You see, can you see my screen? Am I sharing it? Maybe
not yet.
All right. So you see here inside this text file, I have this data, which is the exact data that's in that example.
Yeah.
So I want you to come in here. I want you to copy it out of your text file. And then I want you to run your code, right? And then I want you to, whenever it's prompting for the cashier module, right? Instead of hand typing that data, I want you to do a right click, which will paste it into there. Right. So you see here now, when I do it from the command terminal, it's the system freaks out, right? It doesn't know what I'm doing. But imagine that I'm in my cashier. You see that data is right there, and you see how easy it is for me just to paste that in there instead of Dr. Barnett standing there watching, 20 some students hand type this, and I lose my mind because people are doing typos and not getting the computate, because I can't error check their tax rate very easily, right? So that's what I want you guys to do. Now, look, I know you guys are going to be fine tomorrow. My anticipation is 80% of the rest of the class is going to be a train wreck. Okay, so it's important that we, that we get everybody, and it takes a little bit of time. And anybody that's in here that's had me already, let's see, who's still in here? Felix, so he's not paying attention. George has had me before. They know what I'm talking about, right? There's now at the very end, at the very, very, very end, I give you a file on for your final exam lab portion, which you get like a week early, and you can work on it, for up to a week before it's due. I give you a file of about 125 books.
Oh.
Right? And so you'll be reading that in with the file. Okay.
Yeah.
But here coming soon in a couple of weeks, I have another file that has 20 books in it, but you're not going to be able to open that with the file. I want you to paste that data in there via the add book menu, which I'll show you. We'll talk more about that later. Okay.
Yeah.
Yeah, but you're not going to do any file IO until the very end. Okay.
Yes.
And like I said, it takes a couple of weeks to get accustomed to this. But when you do, you're going to be a stronger programmer, right? You're going to understand the process of compiling and linking, and it's not going to be some black magic that you don't, that you feel intimidated by. And people start talking about compiling and linking and certain compiler flags. As a computer scientist, at some point, right, somewhere along your path, you're going to encounter a situation where you're going to be confronted with it, just in passing or something, or maybe an assignment, and it's important to learn. Now IDEs are important too. Okay, it's just that for me, I want students to learn how to do command line compilations before they, at least some, right? Maybe dual learn that along with an IDE. And then with my 1A students, I don't teach them an IDE at all, right? Because IDEs have their own learning curve as well. Okay.
Yeah, so copy and pasting was like a shortcut to like
data entry.
Yeah.
For the data entry. And it ensures that you don't have any mistakes.
Yeah. Yeah. I think that's all. Thank you.
All right, guys. Okay, folks, I'm still on here. I'm on the hook until 8 o'clock. So I'm going to turn off my mic and turn off my video. So if you guys need anything, just, say something. I'll probably hear it. While I'm here, so George, are you there?
No.
George,
This is not.
Professor, I actually did have a question. But it's actually not about your class. It's just about my enrollment in your class. I just wanted to verify that I'm on your class roster.
For 1D?
For 1D, yes.
Do you have a login for the VM?
Yeah, I do.
So then at least at some point in time you were on the roster, because that's where I got the data from to create your files.
Okay.
But did you drop by mistake or something, or?
No, the reason I ask is because before I enrolled in your class, I was originally in Nadia Ahmed's class. And the reason that is because there was actually a course that overlapped with yours, but I actually got a course overlap request accepted. So I'm actually overlapped. Yeah, I did.
I was told by the dean that they wouldn't do that anymore. So I actually had somebody that actually it was George. George, are you on here?
I am. Hello.
So wasn't it you that had some kind of overlap and you?
Yeah, it was for Math 30B. I couldn't take it here because it was straight overlapping with this class.
Okay.
That's interesting because.
What was the class that you overlapped with?
It was actually CS6A over at IBC, which is CS30A at Saddleback.
Okay, so that's fine.
Yeah, I think IBC is a little bit more lenient with that, because when I emailed them, they were just like, yeah, if the class is completely asynchronous, then overlap should be fine.
Is it the same portal that you use, My Site? Is it the same one for both IVC and Saddleback?
Yeah, yeah, and it's kind of weird because I've been getting Canvas updates and My Site updates from Nadia Ahmed's class, and when I joined her Zoom session, she said that I was on her class roster.
Well, I just checked and you're on mine.
Okay, okay. I just wanted to make sure, and the reason I bring it up is because I don't think there's a chance it's gonna happen, but let's say I drop from Nadia Ahmed's class. I don't know if that's gonna affect my enrollment in your class.
So are you registered in both?
Yeah, I am. It's kind of weird because when I go on My Site shows that I'm only enrolled in your class, but then
Well, that's the authoritative source. So where else are you in Canvas?
yeah. So I thought I thought it might have been a mistake on Canvas's then. But
Yeah, well, it sounds like Canvas. So the authoritative source for your grade and everything is My Site.
okay.
So
Just wanted to confirm that. Yeah, and yeah, the reason I bring it up is because I just wanted to make sure that like at the end of the semester, I'm not getting like an extra grade for a class that I'm not.
No. Because in my Canvas, my section, which is different than Nadia's, your grades will be calculated from within there, and then also grade scope, right?
Okay.
So I'm kind of nervous about this grade scope stuff, but I'm hoping that it's going to drastically cut down my grading time and get you guys quality feedback. So, so we'll see how that runs.
Yeah. Also I'd like to mention that like Nadia, she told me to contact Larry Perez, who I guess is the chairman for the computer science department. Yeah. So I'm just waiting on a reply from him because Nadia said she can't drop me from a roster for some reason. So I was just kind of confused as to why that is.
So she's probably going to put zeros and stuff in there for your assignment. You just ignore it because if she were to go into My Site, if she were to check her My Site, you're not going to be in there.
Okay.
So My Site is where we enter the grades.
Okay. I didn't mention My Site to Nadia. So would you advise that like I go into a Zoom session again and maybe ask her if I'm on there?
Yeah, if she's available, could you ask her to check her My Site to see if you're on there?
Okay. Yeah, that's just that was a little weird to me because these past couple of days I've been getting updates from
But what you probably should also do is just contact the IT bubbas over in is it the BGA or BGS, whatever building that is, for Canvas, for the help desk, and just tell them that they need to remove you from hers.
Okay. Oh yeah, that's like one of the modules on Canvas, right? Like I can just press on one and then
No, I think there is a I'm not sure where the email link is for that. Let's see. Canvas student guides. I'm clicking on now. Let's see. So if you click, and I'm not sure if that link even works for you, but if you go to the home page, and you should see a let's see here.
there is a Canvas help page, but I'm not sure if that's what you're referring to.
Well, see if there's an email on there.
Okay.
Q&A.
I'm pretty sure I'll come across the email soon, but I just wanted to address this because I just want to make sure that there was like no issue with my enrollment in your class.
Not in my class, no.
Okay, just wanted to confirm that.
Sure.
I think I'll keep you updated with what ends up happening.
All right, sure.
Yeah, thank you.
Okay, you're welcome. Felix, your hard drive is screaming right now. All right, I'm going to go ahead and I'm going to end the meeting and come back so that he doesn't overload his hard drive with recording this.
Okay.
I'll be right back, guys.
Gotcha.